So last time we looked at this problem, we found the general solution by setting out the auxiliary equation, 2n squared plus 5n minus 3 equals 0, using the quadratic formula to arrive at the fact that n equals 0.5 or minus 3 here. Okay? And then we put those in to this general solution. So one root is k equals a half, and the other one was k equals minus 3. So that gave us a general solution. And then, if you remember last week, we want to find the particular solution using some initial conditions. We've got two constants to find, a and b. So we need two sets of initial conditions. And luckily, we've got them. When x equals 0, y equals 4. And also when x equals 0, the differential is 9. So we've got two sets of conditions. We need to set up two equations, and we can solve them simultaneously. So putting the first one in, when x equals 0, y equals 4, so that gives us this. And then when we differentiate it, we get this, and putting the other set of conditions in when the differential is 9, when x equals 0. So we can find two equations, 1 and 2, and solve them. And we did that last week. Now this time, let's look at this one. Find a general solution for this. Is this one we did last week? Right, okay, so I hope we have a look at it. Yeah, so in this one, when we put in the values, we notice that the square root turns out to be 0. So this is a case where the roots are equal, and n turns out to be 4/3. Just confirm that for yourself, or that you get that general solution. And if you remember back to last week, if the root is the same, the solution is of this form. So there's our answer, the general solution. Y equals AT plus B, and then e to the 4/3 t outside. So this is the general solution. Now let's go ahead and find a particular solution for this type. Okay. Same sort of procedure. We've got two sets of initial conditions. So let's look back. What are they from the question? We know that when t equals 0, y equals 3, and so does dy by dt. Y equals dy by dt equals 3. So we know that when t equals 0, y equals 3. So you can plug them straight in to the general solution. Write down the formula that you would get. Hopefully you get that y equals 3 equals a times 0 plus b e to the 0, because t equals 0. So the a constant disappears, e to the 0 is 1, and we're just left with b equals 3. So actually, it's very easy to find out what b is. Okay, b equals 3. Now for the second initial condition, we've got that when t equals 0, the differential of y with respect to t equals 3. So we've got to differentiate it. Y equals our general solution, ax, or at rather, plus b, well b equals 3, so we can put 3 in, e to the 0. Oops, no. E to the, what was it, 4/3 t. So that's the general solution. Now with b put in, we could leave it as b, or we can put b in as we know what b is. Now we need to differentiate this. But at this stage, and it always works for examples like this, the problem here is that we've got to differentiate something where t is occurring twice. Look, t is in the bracket and t is also in here. So I've got one function, at plus 3, multiplied by another function, e to the 4/3 of t. And so I need to use the product rule, which tells me that the differential is the first part, which I would call u, multiplied by the differential of the second part, plus the second part multiplied by the differential of the first. The product rule. Use the product rule, which is something we have looked at. The differential of y with respect to t equals u dv by dt plus v du by dt. I never actually bother to write down this product rule while I'm using it in a way, but there it is. What it's saying is, and this is worth making note of, to use the product rule, all we do is multiply the first term, which is in this case the bracket, multiply that by the differential of the second term, which is e to the 4/3 t, plus the second term multiplied by the differential of the first. And effectively, you just remember that little rhyme. The first bit times the differential of the second plus the second bit times the differential of the first means you can write down the answer. dy by dt equals the first bit, at plus 3, times the differential of the second, which is 4/3 e to the 4/3 t, plus the second term, e to the 4/3 t, times the differential of the first bit, which is just a. To make it easier to understand, that's the first bit, u, that's dv by dt, that's the second bit, v, and that's du by dt. So you can see them there, but you wouldn't necessarily write those down as red letters. So the beauty of this is that when you're doing a situation like this, where the roots are equal, remember what this is about, the general solution, at plus b, e to the 4/3 t, we're always going to have to apply this product rule. So once you've learnt it, it's the same every time. With first term multiplied by the differential of the second, plus the second term multiplied by the differential of the first. And now we apply our initial conditions. When t equals 0, dy by dt equals 3. So we can write that 3 equals a times 0, because t equals 0, plus 3 times 4/3 e to the 0 plus e to the 0 times a, which we can tidy up to get 3 equals 3 times 4/3, which is just 4, plus a. Therefore, a equals minus 1. So we've got b equals 3 and a equals minus 1. So we can put them back in to the general solution and write the particular solution. Remember, the general solution is that, and so we can now rewrite that. Y equals at plus b. Oops. E to the 4/3 t. So therefore, the particular solution is y equals a, which was minus 1, and b equals 3. So a equals minus 1 and b equals 3. So we can write b minus t e to the 4/3 t. And that's the particular solution. oops, what's B? 3, isn't it? Yeah, B equals 3. So B equals 3. 3 minus T. E to the 4/3 T. Because A equals minus 1 and B equals 3. So that's the particular solution. Remember why we're doing all this. You know, this question that we've just solved, find a general solution for this, could represent some sort of oscillation. Okay, this is one that we're not likely to get in a way, because if we look at the solution, it turns out that in fact the oscillation is going to rapidly oscillate and then just disappear off the scale, and so this would probably not be an oscillation that we'd be investigating in a real engineering scenario. It certainly wouldn't want this sort of situation. It looks as though that as time is going by, the oscillation goes positive or up and then just shoots down and disappears off. So obviously whatever is going on in this oscillation, it's not oscillating anymore. One of the movements is displacing towards infinity at the end, isn't it? And so let's have a look now at another example. I'm a bit worried about that one. Actually, I might come back and readdress one, make sure I've not made a mistake. And while I'm doing that, because I wasn't expecting to see that, let's leave you with something to have a look at. This page here, I'll print this page out for you, so you've got a copy each, and I'll do that on the printer now. But just in the meantime, have a go at this. So in problems 1 to 3, determine the general solutions. And there are the answers, look. And in problems 4 to 9, find a particular solution given some initial conditions. So I will print this out for you. Okay, so if I just give you a block of time now to have a go. Okay, let's just have a look back at this particular solution. Of course, if I've thought about it, now I've had a chance to think about it, it does make sense, this solution. It's not one you're going to come across generally. And the reason is because this exponential function is positive. E to the 4/3 t means it's an exponential growth, which means this thing is going to get bigger and bigger and bigger, which is effectively what's happening in this curve here at this point. It's getting bigger and bigger and bigger in a negative sense. And that makes sense in a way, because if you look at this part of it, 3 minus t, as t goes by, when t equals 3, 3 minus 3 is 0. So 0 times anything is 0. So in other words, when t equals 3, y equals 0. And that's confirmed here, look. When t equals 3, y equals 0. And then after that point, once t gets greater than 3, 3 minus a number bigger than 3 is going to be negative. So the value of y is always going to be negative. And this exponential growth means it's going to get bigger and bigger in a negative sense, which is exactly what's going on over here. So I would have expected the curve to look like that, but it's not one you're going to come across in an engineering scenario, or if you do, it's certainly something that you don't want. It's some sort of positive feedback situation where whatever y is measuring, voltage or current, is just getting bigger and bigger and bigger exponentially. So you want to avoid that sort of solution when you're modeling an engineering situation. So now we'll leave it that you're going to have a go over this next week or so at some of these questions, putting in the initial values. Bear in mind the 3 possible solutions that we were looking at last week. And next week we'll look at the complex solution in a bit more detail. Okay.